A conflict is brewing at the very core of artificial intelligence. And this isn't a war fought with soldiers, but with fundamental particles. It's the incumbent, the electron, versus the challenger, the photon. This is Tensor Lens, and today we are diving deep into the next substrate for AI computation.
So to really get a handle on this battlefield, we have to start with the first principles. And the fundamental object in all of AI is the tensor. Now, for our discussion today, let's keep it simple. A rank 2 tensor is just a matrix. It's a grid of numbers that can represent pretty much anything, from the pixels in a picture to the weights inside a neural network.
And what is the engine of modern AI? Well, it's just the constant, relentless, brute force multiplication of these matrices over and over again. For decades, we've done this math by shoving electrons through copper wires on silicon chips. But that trusty workhorse, the electron, well, it's starting to hit its physical limits. The heat, the resistance, the insane power consumption. It's all creating a wall that actually threatens to slow down the entire AI revolution.
So this brings us to the fundamental conflict. On one side, you've got the electron. It moves through copper, and its biggest cost is the heat it generates from resistance. Today, its bottleneck is I/O, just getting data on and off the chip and the raw power that takes. It's the entrenched incumbent. But on the other side, you have the photon, a particle of light zipping through a waveguide. Its cost is propagation loss, and its challenges are all about manufacturing and precise control. It is the challenger. And our thesis today is that this challenger is about to have its breakout moment.
So the big question is why now? What makes this moment so different? The reason is a massive shift in the whole landscape of AI. See, for years we were compute-bound. We just couldn't multiply matrices fast enough. Now, thanks to incredible chips like NVIDIA's GPUs, we've solved that. We've actually flipped into an I/O-bound world. The problem isn't doing the math anymore. It's moving all the data to the place where the math needs to happen.
And hey, don't just take my word for it. Ayar Labs, a key company we're going to look at, frames it perfectly. The critical bottleneck facing every single data center and AI cluster out there is data movement. We are spending more energy and more time just shuffling data around than we are actually computing on it. And this is the exact problem that photonics is uniquely positioned to solve.
To really put a number on this, look at this slide. A single, modern 800 gigabit electrical port on a data center switch can chew up to 30 watts of power. Just one port. Now, multiply that by the tens of thousands of ports in a modern AI cluster. The power draw is just astronomical, and most of that energy is literally just wasted as heat fighting electrical resistance. It's unsustainable.
So here's our roadmap for today's analysis. We're going to cover 5 sections. First, the physics of light on a chip. Then, the interconnect imperative. After that, the computing moonshot, the geopolitical battlefield, and finally, we'll wrap it all up with our investment thesis.
All right, first up, the fundamental physics. What in the world is a photonic integrated circuit or a PIC anyway?
Well, at its very heart is this little component right here, a waveguide. The easiest way to think about it is as an optical fiber that's been etched directly onto a silicon chip. It's this tiny channel, just a few hundred nanometers wide, that traps and guides light. And this is where the economic genius comes in, because we can make these using existing CMOS foundry processes. We can tap into decades and billions of dollars of investment in semiconductor manufacturing to build circuits for light.
Okay, but how do you actually compute with a simple waveguide? The key is this incredible structure called a Mach-Zehnder Interferometer, or MZI. What it does is it splits a beam of light, it shifts the phase of one of the paths, and then it recombines them. Now, the physics here is just beautiful. By building a mesh of thousands of these MZIs, you can physically construct any matrix you want. Computation happens literally at the speed of light as photons interfere with each other. And the economics? Staggering. This whole approach promises a theoretical 2 to 3 order of magnitude that's 100 to 1,000 times improvement in efficiency over the best electronic chips.
But of course, it's never that simple. The choice of material you use creates this critical trilemma. Standard silicon on insulator, or SOI, is the go-to because it plugs right into cheap, mature CMOS manufacturing. The problem? It's physics. It's just not very good at emitting or modulating light. On the other end, you have these exotic materials. Lithium niobate has a powerful physical property called the Pockels effect that lets you do ultra-fast modulation, but the economic reality is it's expensive and complicated to integrate. Same thing with materials like indium phosphide. They're great at making lasers, but they come with high costs and big manufacturing risks. So choosing the right material is this constant tug-of-war between physics and economics. Okay, so this brings us to the most immediate, the highest certainty application for photonics, the interconnect imperative. The mission here is really simple. Use light to kill the data movement bottleneck and get rid of what we call the copper tax.
The solution is co-packaged optics, or CPO. Now, instead of having a clunky pluggable module on the edge of a circuit board, CPO puts the optical engine right next to the main processor, on the same package. And the results, based on data NVIDIA showed for its 2025 roadmap, are an absolute revolution. The electrical path shrinks from centimeters down to millimeters. Signal loss just plummets from 22 decibels to just 4. And remember that 30-watt port we talked about? It drops to just 9 watts. That is a 3.5 times efficiency gain practically overnight. This isn't theoretical. This is a planned product.
In the market, it's validating this thesis with a torrent of capital. Ayar Labs, which is focused on a universal optical I/O chiplet, has pulled in over $370 million from a who's who of investors: Intel, NVIDIA, and AMD. Meanwhile, Celestial AI, targeting memory interconnects, raised over $500 million before being snatched up by Marvell in 2025 for a whopping $3.25 billion. This is a commercial reality. With NVIDIA committing to CPO for its 2026 platforms and Marvell projecting this will be a billion-dollar business by 2029, the question of if optical I/O will happen is totally settled. The only question now is who's going to dominate the space.
So, interconnects are a near-term certainty. But now, let's talk about the Moonshot. This is the far more ambitious, high-risk, high-reward goal of not just connecting chips with light, but actually computing with light. The promise here is analog computing at a scale we have never seen before. A landmark paper in Nature in 2025 showed off a photonic accelerator with over 16,000 components on a single chip. It was doing matrix operations at 1 gigahertz with a latency of just 3 nanoseconds. And this isn't just happening in a lab. This is the promise that has allowed startups like Lightmatter to raise $850 million in venture capital. They are not chasing small, incremental gains. They're going after orders of magnitude improvements over the very best GPUs. But, and this is absolutely critical, the same paper that showcased this incredible potential also delivered a huge dose of reality. The authors themselves state that the main obstacles aren't theoretical, they are practical. It's immature manufacturing and a lack of advanced packaging. We know the physics works. The real challenge is engineering it so it's reliable and can be built at scale. So what's the pragmatic path forward? Well, it's a hybrid approach. You use photonics for what it does best: massive parallel matrix multiplication. That's your photonic core. Then you convert the signal back to the electrical domain, where mature, reliable CMOS logic handles all the nonlinear stuff, like activation functions and memory control. This hybrid approach really gives you the best of both worlds, and it's almost certainly the fastest path to commercialization. Now let's zoom out from the tech itself and look at the broader industry. Where is the money going? Who are the key players? And what are the geopolitical forces shaping all of this?
The M&A activity is sending a crystal clear signal. When Marvell buys Celestial AI for $3.25 billion, they're doing it to integrate optical I/O directly into their data center products. When a huge foundry like GlobalFoundries acquires AMF, their stated goal is to become a leader in this space. And the crucial takeaway here is the exit strategy. For most of these startups, the goal isn't to IPO, it's to be acquired. The big semiconductor incumbents need this technology to stay competitive, and it's way faster and less risky for them to just buy a specialized team than to try and build this incredibly complex capability from scratch.
And of course, a technology this important inevitably becomes a geopolitical issue. A 2024 report from the Center for Strategic and International Studies calls Silicon Photonics a new frontier in the tech competition between the US and China. Think about it. US export controls on high-end GPUs are creating a massive incentive for Chinese firms to just bypass the electronic route entirely and invest heavily in their own homegrown photonic accelerators. It's a way to leapfrog the current paradigm.
Which brings us to our final section, the Tensor Lens verdict. How do we pull all of this together into a clear, actionable way to think about this space? Well, we see it as a two-pronged thesis. Path 1 is your core position. This is the high certainty play. We're talking about optical I/O and co-packaged optics. The technology solves a real, painful, proven bottleneck. The timeline is clear, with NVIDIA deploying it as early as 2026. So the thesis is simple. This is an essential infrastructure upgrade, not some optional feature. The action then is to invest in the picks and shovels of this revolution. The enablers like Ayar Labs, who make the core tech, and the foundries like GlobalFoundries, who are going to manufacture it at scale.
Path 2 is your satellite position. This is the high-risk, high-reward bet on pure photonic computing. The potential here is a true paradigm shift, a 100x or more improvement in performance per watt. But the hurdles are massive. Manufacturing and packaging are tough enough, but controlling these analog systems, making sure light behaves with perfect precision without the clean ones and zeros of digital logic, that's another challenge entirely. So this is a classic venture style, all or nothing bet. The action here is to place smaller, calculated bets on the absolute best teams, like Light Matter, and you make that investment contingent on them landing a concrete design win with a major cloud provider.
So here's our final prediction. By 2028, co-packaged optics and optical chiplets will be a standard, non-negotiable part of any high-performance AI hardware. That part of the story we think is already written. The much more exciting and still unanswered question is who will be the first to truly and reliably teach light not just to communicate, but to compute.
For more rigorous analysis at the intersection of semiconductors, physics, and finance, make sure you subscribe to Tensor Lens.
This is Tensor Lens. Analysis, not assertion.